Back in 1981, Jack Sepkoski divided up the animal fossil record into three major components: the Cambrian, Paleozoic, and modern evolutionary faunas. These have become a staple for understanding the history of life, but what exactly are they? 40 years later, do they still stand up? And what exactly does the concept of an evolutionary fauna even mean? Let's have a close look. Hello everyone. So after I posted the last video, which had the weird black borders around, sorry about that, won't happen again, suddenly realised that was my 100th video. In less than a year. I'm quite excited by that. Yeah, so I doubt I'll be doing 200 by the end of the second year, but you never know. But yeah, I kind of missed that because of all the members' videos as well sort of add up to 100, apparently. So this is now the 101st. Anyway, one of the things I've been asked about a few times is when I've posted little summary diagrams showing the diversity of life through time, there's quite often labelling on it about the Cambrian, Paleozoic and modern faunas. And so I thought this was worth a bit of a deep dive in terms of trying to understand why we have this concept, why it's useful potentially, and how accurate it might actually be. So this is going back to what you'd think would be one of the fundamental aspects of trying to describe the history of life, is plotting how diversity patterns have changed through time. You think that would be easy, right? Definitely. You just add up all the fossils. However, there are lots and lots of fossils that have been described in numerous languages around the world, in numerous alphabets. There is no single database repository where all of it has been put in and you can just get it to spit out the numbers. It's actually not an easy thing to do. And that's even for the described fossil record, the things that have actually made it into papers. So trying to assess the diversity of life through time is full of all sorts of problems, difficulties. And when you start looking at things like biases, such as taphonomic biases, reasons why the preservation of one group is different, perhaps at different times, as well as in different continents or in different environments, there's so much that feeds into our understanding of whether the fossil record is A, accurate, and B, accurately described. Nonetheless, we have a broad outline. And this broad outline actually goes back to about 1860. The first sort of summary of the diversity of life through time was by a guy called John Phillips. And it was a pretty crude diagram, but it showed several components which are still recognizable in the curves today, which is amazing, really. So he showed that there was overall an increasing trend of diversity through time, with the modern world being the top of this diagram, that you have a couple of sort of major dips in the history, one at the end of the Mesozoic, so that became the Cretaceous Tertiary boundary, and one at the end of the Paleozoic, which is the Permo-Triassic boundary. Both of these are now recognised as significant mass extinction events, especially the end of the Paleozoic. And then during the Paleozoic, he's got a couple of waves, which includes a sort of sudden increase and then a bit of fluctuation and another peak later on. And this is largely the sort of pattern that we see today, especially when you don't allow for various biases, which we now understand better. So basically, the older the rocks, the less chance there is of any one thing being fossilized and preserved and exposed. Partly it's because there's not so much rock of that age. A lot of it has been eroded or metamorphosed during the time between it being formed and today. So you tend to get a bias towards more recent deposits and more recent organisms. So the Cenozoic life is much better known in many ways because there's lots of rock deposits which have not been metamorphosed and which have not been dissolved and all the rest of it. So you have a really good fossil record which gets gradually worse in general as you go back. So that was 1860. That was John Phillips, and it took until probably about 1980 before we started getting a much better picture of the diversity of life through time. And we really had to wait until the work of Jack Sepkoski, who was the first, as far as I know, to start trying to approach this on a big database sort of scale. This was the early days of computing as well, of course, so you had the potential for software, analytical tools, and that sort of thing. And what he did was compile huge amounts of information from the published literature. I mean, one of his papers was called 10 Years in the Library, and then something about confirming the previous patterns. So he spent a lot of time just trawling through all of the published work, extracting information, compiling massive databases, and then looking for the patterns that existed. And it wasn't just a crude blunt instrument sort of approach. He started to analyze his data in interesting ways as well. And that leads us on to the idea of the evolutionary faunas. So it's important to realize what exactly he was using. This was the published data up to 1980-ish, probably in the 70s actually. He must have taken years to compile it. And it probably didn't include a lot of obscure literature from China and Russia because he was working in America, and I'm not sure how much access he had to those data or how much he understood the language, for example. So I think this is mainly based largely on the Western world and didn't include all of the literature, but it was still an incredibly thorough job of what was known at the time. But when I say known, I mean what was published. And of course, most of the time we go out looking for fossils, we may well find new things, but we can't necessarily describe them. See the last video when we were looking at all these lovely bits of the Harned Shale, where we're fairly confident there are quite a lot of undescribed species in there, mainly bryozoans and ostracods. And so those aren't in the literature. And unless I somehow get round to publishing anything on them, which seems highly unlikely, it seems that they probably won't get into the literature for a good long time until someone with an interest or specialism in one of those groups actually goes back to some of these sites and starts writing papers on them. So there is a lot of material out there in museums, in private collections, and which are just never been worked up. So the published fossil record is biased toward things which are most easily publishable. So the bryozoans, for example, that I mentioned, we have this gorgeous fauna, but they're not preserved in the right way for bryozoan taxonomy. So they're probably not even describable in terms of being able to be published and given names. So that starts to feed into all sorts of problems about the quality of the initial data set, but it's the best we got. So we'll come back more to some of the limitations of the data and the analyses in future, but this is what we're looking at. It is the published data set up to that point. And what he did was compile all the records that he could find of all of the different classes of animals, not counting plants, not counting the modern world, because aside from anything else, there are something like 100 classes of soft-bodied things that have no fossil record. And not counting the ediacarans, because they have a very weird and different pattern, so he just sort of cut them off entirely, which, given that we don't know what they are, is actually quite reasonable. So this is the animal fossil record, and it's dominated by marine things, simply because the marine world is mostly what gets fossilized. He then constructed this data set of the families and orders within classes and the occurrence data based on the known ages of all of these fossils and created a massive great data matrix, which is a good start. You can then do whatever you want with a data matrix. And this is where I and many other paleontologists get a little bit sketchy because, personally speaking, my statistical understanding and skills are not up to doing a full critique of exactly what he's done. I understand some of the concepts, but when it gets into the eigenvalues and things like that, I start getting a little bit hazy. And I realized when I was trying to sort of plan out this video that I can't actually explain to you exactly what the mathematical process is and why this is the best option. But I do know what the process aims to achieve, so I can explain that much. I'm sure there'll be some of you out there who have a much better understanding of these things than I do, but bear with me for those who do, because that isn't my skill set. So, okay, what he's done is factor analysis. Now, factor analysis and its equivalent, which is called principal components analysis, it's the same sort of idea, is a technique which allows you to take a large multi-dimensional data set. So not something you can plot on a 2D or 3D graph, but multi-dimensional, with all sorts of different components all feeding into it, which may have influences on each other and may all contribute towards an overarching pattern, which is the diversity of life. So what this sort of factor analysis does is look for common threads. It looks for elements of the data set that explain most of the variation inherent within that data set. You can't get a small number of factors which explain everything, or you wouldn't need all those other factors. But it can extract the components of the diversity of the data set that are the most important in dictating the patterns that come out of it. So you can simply show a graph of the diversity of life through time, and you end up with Sepkoski's classic curve. This is one that has been repeated in the literature hundreds, if not thousands of times. It's a fundamental of our understanding. And there have been upgrades to this since, which I'll get into later, but this is the basic pattern. And you can see it's very similar to John Phillips's idea. But in a case like this, you can see there's a lot more fine detail, and it is based on actual numbers. But you can still see there is this initial sort of rise in the Cambrian, then a large peak to a plateau in the Palaeozoic, huge great drop at the end of the Permian going into the Triassic, another great rise up in the Mesozoic, another drop at the end of the Mesozoic, and the rise again. So we've got this gradual trend towards higher diversity. We've got the same big drops at the mass extinctions, and we have the same overall shape of it. But Sepkoski wanted to do more, and hence the factor analysis. So he was looking at the diversity curves of all of these groups, the timings of the occurrences of families within all these classes, and factored the data in terms of the classes. I'll just go through a little bit, reading out a bit of his techniques, just so you get a vague idea. The mechanics basically involve computing the eigenvectors of the matrix of cross products of all normalized samples, then determining how many of these eigenvectors are important by examining the magnitude of the associated eigenvalues, which can be conceptualized as the averages of the loadings on each factor, and finally rotating the selected eigenvectors to simple structure or end-member configuration. Rotation is necessary in an analysis like this, obviously, because it avoids the nonsense associations that appear in raw eigenvectors. For example, the first eigenvector for the data in figure 1 would represent the average fauna of the entire figure, and thus would include positive contributions to both trilobites and marine mammals. Rotation, however, would segregate these classes onto separate factors, properly reflecting their complete lack of stratigraphic overlap. Hopefully, some of you have got at least a vague idea of what that is trying to achieve. There's a lot more to the methods, but it's a way of analysing the contributions of these different components of the diversity to the overall diversity while keeping them separate in terms of their stratigraphy. You get the idea, hopefully. So that's what the analysis does. And when he did this, he found that there were three primary factors. These were basically groups of classes that clustered together and explained, I can't remember, it was more than 90% of the total variability in the dataset. So the total diversity curve can be almost entirely explained by a combination of three factors. These factors are the evolutionary faunas. So we have factor one is an association of classes such as the trilobites, the lingulate brachiopods, monoplacophthons, which occur primarily in the Cambrian and then declined. Factor two is a series of other things like stenolemate bryozoans and crinoids and so on, articulate brachiopods as they were then, the calcite-shelled ones, which diversified dramatically in the Ordovician, declined dramatically at the end Permian, and then sort of managed to carry on a little bit since then. And then the third factor is the modern fauna, which is characteristic of the groups that dominate the world today and started to take over on a large scale during the Mesozoic. So many of them have ancient roots going back to the Cambrian or Ordovician, but these are classes that really took off in the Mesozoic. And so we have this mathematical approach, which is therefore not subjective. It is basically an analysis of the data that were available, and it has generated a series of groupings of classes of animals which appear to show parallel patterns in the sense that you have some of them diversifying and proliferating and being successful in the Cambrian, then being replaced by a Paleozoic evolutionary fauna, which is dominated by these other ones, and then those were replaced by a modern evolutionary fauna. Okay, that is the fundamental basis for the concept of evolutionary faunas. It's a mathematical construction based on our data, which seems to show that there are consistent patterns, which means that certain groups of organisms were very successful at different times in the past, and they have replaced each other in phases through the fossil record. So this is a classic case of scientific reductionism in its good and bad senses. So what we're doing here is taking an extremely complex array of data and extracting a pattern. Now, it doesn't necessarily follow that that pattern is strictly telling us a clear truth. What does it actually mean? When you have an evolutionary fauna of multiple groups that seem to show, in combination, a consistent diversity profile through time, does that mean that these groups were evolving in lockstep with each other and therefore there were similar ecological pressures, or they had adapted to them in certain ways such that you can get a clear pattern of diversification that was consistent? Or is there something else going on? Because in a sense, this is also a bit of a crude sort of methodology, because within each of these evolutionary faunas, we are not seeing any breakdown. We're not seeing whether the contributions of the different classes to that fauna is consistent. There may be a whole stack of really complex dynamics going on within this wider group that is hidden by the fact that in combination they generate a large part of the pattern. And when you have lots of components which you are condensing down to 3 components, it may be that it is oversimplifying in a way that is actually not helpful. It might potentially be giving us an impression of simplicity and consistency amongst the members of this evolutionary fauna that is not really necessarily true. It's something to bear in mind. Reductionism works both ways. It shows us patterns that are hidden, but sometimes it hides patterns that are there. Okay. How much of this is dependent on the data itself, themselves? The potential for long-term biases is actually quite important here because of several factors. One is that taxonomy is not consistent through the Phanerozoic. Taxonomy is an artificial breakdown, subdivision of the diversity of life that we have imposed to be able to talk about it. Where we know a group better, the taxonomy is better developed and more highly broken down. So in a group that is really well known, say Cenozoic bivalves, modern bivalves, same sort of thing basically. We have subdivided that into numerous families because we know the taxonomy, we know the diversity really well, and we can actually recognize many, many groups within the bivalves. If you go back to the Palaeozoic, we don't know bivalves anything like as well because we don't have the same type of preservation. The fossils are quite often preserved as molds, which don't show you the level of detail you want. In many cases, they're just not described at all, and the fossils are relatively few because there's not so much rock of that age, and the environments that they lived in were more limited, and those environments tended to be erosional. And so you have a much smaller pool of information, and even lower proportion of that has been described. We don't understand it as well. And therefore, it's not going to be divided into families, for example, at the same level as the modern ones are. And this applies to many groups. As you go back through the fossil record, our knowledge of the taxonomy becomes poorer, less well developed. And so at any stage in time, there is less subdivision. So this is potentially a major bias towards certain groups in particular, but most groups, having greater subdivision and more diversity at family level in the more recent rocks. And this is actually something that we have to take seriously because part of that general expanding diversity going up towards the modern is going to be related to the lack of knowledge that we have for previous ecosystems. There are other problems as well, though. Taphonomy itself shows long-term trends. There are changes in seawater chemistry that make calcite or aragonite more stable, for example, and that leads to problems in which groups tend to be preserved at different times, at least preserved better. There are problems just with the environments that have been preserved. Think about, for example, the deep sea. That's not really preserved much at all, but you do get traces of the deep ocean communities in hydrothermal vent communities that have been preserved at various points going back to Devonian or something like that, I think it is. And these are very limited pockets of ocean crusts that are scraped up onto the continental crust. But most of the time when that happens, it also gets metamorphosed, because that tends to be the result of a subduction zone, which then ends up in a mountain building event, which then destroys everything from the older rocks. It's one of many, many examples of biases relating to taphonomy. So the other thing is that these data are from 1980. People have been carrying on doing lots more taxonomy, and the databases have increased in scope and in fidelity and so on over time. There is a Chinese database now which is focused more on that, but it's also global in the same way that the American one is global but focuses more on the Western side. there's all these factors. So the Sepkoski curves for diversity are not the last word, and they have been superseded now to some extent, or at least expanded upon by more recent work. So does that confirm the same overall patterns that he was seeing? Kind of. Now, a lot of these studies are even more technical and sophisticated analytically than the Sepkoski stuff is, as you might expect. But there have been quite a few analyses and new data sets and new treatments of data sets that have given us more information. So John Alroy, for example, in 2010, in addition to quite a lot of complex analyses looking at latitudinal belts and things like that, has also tried to standardize for the sampling intensity for the different intervals. So whether this is due to the exposed rock area or just the amount of sampling that has been done in a particular area or particular time period, it's all been incorporated into this and then tried to be standardized to give you a way to remove the bias that might be there based on the amount of sampling. And when you do that, one thing that is really striking is that going back to at least a sort of middle Cambrian, a lot of that gradual increase into the modern disappears. You've got a rise since the Permo-Triassic, which is kind of stepped up and down at various points. The mass extinctions still are mass extincting, but there is no clear overall trend. And the peaks in the diversity during the Palaeozoic, including in the Ordovician Silurian and in the Permian, are actually very similar to the highest peaks that we get in the Cretaceous. So this suggests that the overall diversity patterns are biased, and it's quite difficult to remove those biases because we can only sort of retroactively apply procedures that estimate what those biases are and then correct for them. But when you do that, you end up with this sort of pattern here. And you'll notice also that it doesn't look like the Paleozoic evolutionary fauna dominates the Paleozoic diversity. It looks like it is very much more even, at many times at least, between the modern fauna and the Cambrian fauna. It is not a really striking trend where that community just dominated. At some points in the Mesozoic, members of the Paleozoic fauna are actually as diverse as they were at the low points in their diversity during the Paleozoic. It's not anything like as clear-cut a pattern. Okay, so that's interesting. Alroy again, actually, in 2004, was also looking at volatility, proportional volatility. So this is basically how volatile the proportions are going through time. And I don't fully understand exactly what this is showing us, but what he was showing is that there are radical differences in the volatility of the different evolutionary faunas at different times. And this implies that there was actually a lot more complexity going on, including sort of pairwise, so relationships between two different groups which are affecting each other, rather than there being some extrinsic external factor that just affected everything. It's a complex picture, this one, but it basically is partly inconsistent with the idea that there were these temporally dictated evolutionary faunas. There's other things going on, is what he could get out of this one. Then we can go on to a 2020 paper by Fan et al. This is based on the Chinese database, the GBDB, Geobiodiversity Database, I think it was, which is global in its scope, but it is very strongly focused on Chinese work, at least initially. It is expanding rapidly, so it's not only Chinese by any means, but that is a focus. And what this does is it's based on geological sections, so the records of all the species through long sections of rock, and then combining all of these thousands of sections together with machine learning and various algorithms to try to extract the very detailed correlation of the sections and the total diversity on an extremely fine timescale. So we're looking at timescales down to 26,000 years of resolution potentially, which is much, much finer than the timescale resolution that we get in the Sepkoski curves, for example, which are sort of several million year bins. And what you see is, again, a sort of a very similar overall pattern for the Paleozoic, but with a great big spike in the Ordovician and then later on again in the Permian. So a lot of this is similar, and you can trace the diversity of different groups through this interval. And one thing that you see when you do that is that there is an enormous difference from one time period to another of the groups that are making up the largest chunks of these evolutionary faunas. So, I mean, the Cambrian is there, and we see this in the trilobite diversity, which is still high in the Ordovician but gradually declining. And what else we got there? The I think that's others actually. So the trilobites are dominating the role of the Cambrian evolutionary fauna, but then that carries on through the Ordovician and later. The Paleozoic evolutionary fauna is dominated, this is at species level, I should say, not genus or family, at species level by graptolites in the Ordovician particularly. And then if you look in the Carboniferous and Permian, the largest groups are things like Foraminifera, which is a group of microfossils that I don't think was even included in Sepkoski's curves. But then the balance of the different groups is also very different in the Silurian Devonian, through the Carboniferous, through the Ordovician. What we're seeing is that there is no greatly consistent pattern going on here at all. It's also quite interesting. They plot the species and genus curves against each other. So you can see that the ratio of species to genera changes. And at times, there are many more proportionally genera per species than there are at others. And that is going to be an indication of how complete the recording is, you would think, although it might also be related to rapid diversifications which are going past the species level in terms of morphological difference. So again, unclear exactly what that's telling you, but it's an interesting pattern that shows there's another level to look at beyond the surface level of detail. And finally, we have a paper by Rojas et al. From 2021, which is a multi-scale view of the Phanerozoic fossil record, reveals 3 major biotic transitions. So one of the main contributions of this is to add a 4th evolutionary fauna, which is the modern one, and then the Mesozoic is separated from that. So rather than just being a continuous one, there is a distinct sort of Cenozoic to modern one. And the overturn that they were finding is at the end of the Cambrian, as you'd expect, the end Permian, as you'd expect, and then the mid-Cretaceous is another point of overturn, which is unexpected. That isn't at the mass extinction. They're seeing a large amount of overturn from the Mesozoic to the Cenozoic faunas happening before the end of the Mesozoic. This was a paper that's actually much less accessible for people who just want to look at the trends, because it was done by network analyses and things like that. So it would take a long time for me to get my head around exactly what that paper was saying, but it's certainly interesting. But where does this leave us overall? We're seeing lots of reasons for that original distinction of evolutionary faunas into these 3 major divisions, the Cambrian, Paleozoic, and modern, but including Mesozoic, to not actually work when you're looking on a detailed scale. It also breaks down when you look in at particular groups. So Jonathan Adrain et al. In 1998 published a paper looking at trilobites and finding that some groups of trilobites are clearly part of the Paleozoic fauna and others are part of the Cambrian fauna. So you can't divide it up by class level even if you're looking for that sort of pattern. And when you start trying to break down the groups to finer and finer levels in order to match up your groups of organisms into particular larger groupings, at what point does it all become a bit nonsensical? At what point do you just say, well, these species are the Paleozoic fauna because they were there in the Paleozoic? You can start to get so bogged down in trying to find a pattern that's not really there that it is possible that you actually start creating an entire landscape of patterns that are effectively random. What I'm worried about here is that the whole thing might be that we are looking at noise, and we're trying to turn that noise into a signal by forcing it into signal-like shapes by chopping up bits of the noise until they fit into packages. Now, I'm not saying that this has no useful purpose whatsoever. It's certainly been very useful for us to be able to talk about these evolutionary faunas and to give us things to test and patterns to look at. But are they actually telling us anything really reliable? Or are we better off ignoring the evolutionary faunas and just focusing on the groups that we're interested in? Because clearly the pattern is much more complex than a suite of classes that all evolved at the same time in the same way and diversified and then declined and were replaced by other ones. We can certainly see that some groups of organisms, say bivalves for example, really diversified during the Mesozoic, but they were there in the Paleozoic and they were diversifying. So to try to simplify that to a pattern in which things were first just clinging on and not really doing anything, and then the time was right and they exploded in diversity, in general that may be misleading. That's not actually the pattern that there is, but when you try to fit them into things like evolutionary faunas, that pattern starts getting imposed on them. I think it's one of these cases where simplification is not necessarily in our best interests. That reductionism is actually kind of going the wrong way because there is no pattern there to reduce to. You could think of it being a layer on top. It's not reductionism in some ways. The data are there. We have our data, flawed as we know it is, biased as we know it is. We can understand those flaws and biases to some extent as long as we don't conflate things together and hide them. But when we try to superimpose patterns on top of that, we can start to go off the rails a little bit. And I am worried that there is this trend in modern paleontology in general, to some extent, to look for these large-scale analytical results and aim for that simple solution, when in fact that simple solution is being imposed on those results. And the results should be simply the data themselves. Maybe there are nice, clear patterns to look for, but in the case of the evolutionary faunas, I don't think those patterns are nice and clear. I think that the history of life is a huge, great mess. It is complex. It is wonderfully diverse and tangled. You get all sorts of ecological escalations and extinctions. Everything is going on through that history. And some groups do well at certain times and start to diversify. Others do well at other times. Others co-evolve. And trying to extricate ourselves from that messiness, I fear misses the point. We have a tendency to want the answers to be simple. And sometimes, especially for the history of life, the answers ain't simple at all. There you go. I'm very aware that this was an extremely graph-heavy video. Sorry about that. It's just the nature of this sort of bit of paleontology. But there's so much that feeds into understanding this sort of concept that I think is really important for us to cover it, because I am kind of a bit of a skeptic of the big data type approach to paleontology. Yes, you can get stuff out of combining all the evidence together, but I also think there are huge dangers in it. And most critically, I don't think we yet have the data to be able to do a lot of these things. And sometimes you see projects proposed or even published which are based on a particular database, say the paleobiology database. And my reaction is always, but you can't say that from those data, because those data are so incomplete for these groups, these times, whatever it is, that we simply do not know. And there is an assumption fairly widespread in paleontology that we're now at the point of having done all this data gathering. We've done all that now. We can just focus on analysing it. But there is so much new turning up in paleontology all the time that I don't believe it. There is still so much yet to discover. And that, of course, is, for me, a big part of the joy of paleontology, and I suspect probably for some of you too. So, yeah, we'll get on to something else again soon. Not sure what I'm doing next. It'll be a surprise to me too. But see you then.